Alright, this is another video on graphing rational functions, and this is the type of function that you probably have not seen in Algebra 2, and so I wanted to do this video separately because I wanted to draw your attention to sort of what's different about this type of function. Okay, so let's just go through the basics. We have to graph a rational function. The first thing we want to think about is factoring. Factoring the top and the bottom, that's how we get all our information. So the bottom's done, and when we factor the top, we get x minus 2x plus 1. Okay, so far so good. So now we look at our function and try to identify what the key pieces are. So what are the zeros? Well, remember the zeros occur when the function itself equals 0. And the function equals 0, well, you can multiply both sides of this by x plus 3, and that will leave you with x plus 1 times x minus 2 equals 0, and from there I think you can understand that the zeros are negative 1, 0, and 2, 0. Those are the two zeros. Vertical asymptotes. Well, the vertical asymptotes occur when your denominator, the x values of which your denominator equals 0. And so it looks like x plus 3, that equals 0 when x equals negative 3. So the vertical asymptote is x equals negative 3. There are no holes because no factors canceled out. And our y-intercept we get by plugging 0 into the function. So our y-intercept would be f of 0 equals 0 squared minus 0 minus 2 divided by 0 plus 3. And notice all these zeros go away, we're left with a negative 2/3. So that means the y-intercept is 0, negative 2/3. So far there's nothing, I don't think there's anything new. This is what's new. End behavior. So let's talk for a second about end behavior. What's our go-to rule when we're trying to analyze end behavior? The go-to rule is to think of a big number and plug it in. Now I've tried to make the point that when it comes to polynomials, and again, so like this numerator is a polynomial and this denominator is a polynomial, the function itself is a rational function, but just with polynomials, you can analyze their end behavior by just looking at that leading term. Because in the long run, when you take big numbers and you square them, and then, for instance, a billion squared minus a billion minus 2, it's the billion squared that contributes most to the number. So in the long run, what's contributing most to the number is that first term. So you can sort of do your analysis on that. And similarly for this denominator. So this function really is going to behave, in the long run, this f of x, is going to behave basically like x squared divided by x in the long run. Right, now if you think about it, so now let's just think about plugging in a big number. If you take like a million cubed, or I'm sorry, a million, let's just do 1,000, 1,000 squared, and divide that by 1,000, we all know that's going to be 1,000. Right, it's a really big number. Now if you plug in like a trillion squared divided by a trillion, you're going to get a trillion. So the point is, as x goes to infinity, f of x goes to infinity as well. The function goes to infinity, and that'll determine our end behavior asymptote. So as x goes to infinity, the function goes to infinity. What about as x goes to negative infinity? Well, as x goes to negative infinity, you're plugging in numbers like negative 1,000, so like negative 1,000 squared divided by negative 1,000. The top is a positive number, the bottom's negative, and it ends up giving you negative 1,000. So as x goes to infinity, as x goes to negative infinity, then f of x is going towards negative infinity. Okay, so that process we just did works for anything, right? If you just imagine plugging in big numbers, big positive and big negative numbers. Now, here's the idea, or here's the sort of the catch. When we sketch this, it turns out that the function goes off to infinity, but not in like a random way. It actually follows an asymptote. And so our goal is to find that asymptote in order to answer this question, the end behavior asymptote. The end behavior asymptotes you've seen have often been horizontal, but this one ends up not being horizontal. So we're going to see that in a second. Now, just as a sort of review, note that I can take a number like 10 fourths, right? And that's written in improper form. I can rewrite this in another way. I can write this as, well, how many times does 4 go into 10? It goes in 2 whole times, and then there's 2 left over, so it's 2 and 2 fourths, which really means 2 plus 2 fourths, if you think about it, right? We don't always write the plus, but that's what it means. So there are benefits to writing, numbers like this in improper form, and then sometimes there's benefits to writing it like this. We can do the same thing with these rational functions here. And in this case, there's a benefit to writing this rational function sort of in this way right here. So that's what we're going to do. And watch what we see. So how do I write it in this way? Well, in order to write 10 fourths as a mixed number is what we call it, I had to do division, right? 10 divided by 4. I had to know how many times 4 goes into 10. So we're going to do division the way we know how on this rational function. So dividing x squared minus x minus 2 by x plus 3, we're going to use synthetic division. So we'll put the negative 3 in the box. 1, negative 1, negative 2. And let's see what we get. So there's my remainder. So when we decode this, and you guys should know how to decode this, that means that when you divide this out, and I'm going to erase this. By the way, so we have a few representations of this function. Here's it sort of in its normal standard form. We have it in factored form, but using the division here we just did, I could also write it as x minus 4, right? X minus 4 plus, now what's the remainder? It was 10 divided by what we divided into the number, right? Remember, the 4 was what we divided by, and that was the numerator, so it's going to be over x plus 3. So now, think about it this way. Draw your attention to this representation of that rational function. As x goes to infinity, what happens to this piece right here? Well, this piece, the denominator has an x in it. The denominator is going to get really, really big. So this piece is going to 0. So as x goes to infinity, this function is really like x minus 4 plus essentially 0. And so the point is, our asymptote is this guy right here, x minus 4. That's the end behavior asymptote. That 10 over x plus 3 is going towards 0 as x gets really big. And your function just starts to behave basically like the line x minus 4. Now, it doesn't behave exactly like it because you've got this piece here sort of always keeping it away from it. But it behaves like x minus 4. So your end behavior asymptote is coming from right there. Y equals x minus 4. And so that's what we write here. All right, and so now we're ready to graph it. And that's sort of the last piece after all this analysis. I've got my 0 at negative 1, 0, and 2, 0. I've got a vertical asymptote at x equals negative 3. I've got no holes. I've got y-intercept at 0, negative 2/3, so roughly here. Now my end behavior asymptote is y equals x minus 4, so that has a y-intercept of negative 4 and a slope of 1. Now just keep in mind, I don't want to make this a straight. I need to dash this, right? Because it's an asymptote, so it's not actually part of the graph. It's an invisible line that guides the graph. So I'm just going to dash in the asymptote. Okay, and I'm gonna erase this because it's kind of in the way. And now we're ready to graph it. So now we just sort of use our reasoning. We know the graph has to go through these 3 points. It's got to behave the way we know graphs behave around asymptotes, so it's got to be doing this. And now the natural question is, what's it doing to the left of this vertical asymptote? Well, again, I want you to appeal to your reasoning. It can't be doing something like this. And we talked about this in class. It can't be doing that because if that happened, there'd be another 0. But there is no other 0. We would have found it, so it can't be doing that. Okay, turns out it's doing this. And so there you have it. There is a rational function with what we call a slant asymptote. A slant asymptote. Okay, so in this whole video, I think that's the real new piece to you, is that we have to do synthetic division to figure out what that asymptote is.